This is the STEM and curriculum links to the Catapult. So the STEM curriculum links are for science, exploring energy transformation, so potential to kinetic and the laws of motion. And for mathematics, students measuring angles and trajectories or use the algebraic formulas to calculate velocity. Technology and engineering through designing and optimizing the arm and base for precision and power. Now where it gets more interesting is the 21st century learning. So for the intrapersonal, you've got students demonstrating resilience and persistence by troubleshooting and refining their designs. So if it doesn't work the first time, they figure something out to make it better and go further. That can be done by adjusting the tension or arm length and learning that iteration leads to improvement. For the global collaborator, the project encourages students to explore the historical and global significance of engineering, from medieval siege weapons to modern applications like ballistics. You can also use fantasy things like Lord of the Rings, where they've got those massive catapults in the final battle. They can also share designs and results online, fostering collaboration and ethical understanding of engineering advancements. For interpersonal, building the Moving on, we've got my personal favourite, which is the Whirlybird, something that can be done in primary school classrooms, kinder classrooms with care, and maybe having pre-cut the Whirlybirds for the younger students, or even in a Year 12 classroom, either as a fun activity or a way to showcase how physics works. So for science, we are going to be focusing on Year 8s and 9s for this one as well. For science, we investigate air resistance, gravity and energy transfer, mathematics, exploring variables like surface area and rotation speed, technology and engineering with a focus on optimizing blade angles and material choices for better performance. Does cardboard fly better than a piece of paper? Does a mix of cardboard and paper fly better than just one or the other? That sort of things. For 21st century learning, we've got the intrapersonal, students building resilience by testing and redesigning their Whirlybirds. They learn how to manage setbacks with initial trials fail and reflect on how perseverance improves outcomes. So for example, some students will get the angles wrong. They will either have them both going the same way or two going backwards, for example, and it won't work. It will just kind of flop down and not spin the way it's supposed to, and they will have to work to figure it out and make it work. For our global collaborators, the activity provides a platform for students to explore global applications of flight technology, for example, drones in disaster relief, sharing their findings in collaborative digital spaces, fostering ethical and ICT skills while broadening their understanding of sustainability. So doing research and really getting those students involved in even trying things like the Windows Flight Simulator, getting some of those ICT skills in with also doing the more physical tasks. For interpersonal, we've got working in teams, students discussing and refining designs, sharing feedback on how blade length or material affects flight, and the collaborative approach teaching effective communication and adaptability, and just working on those skills in general. So you can have teams going away and you can ask them to focus on how different designs fly and to really dig into that and experiment. So for critical and creative thinking, students experiment with different designs to optimize flight time and analyze the results. Creative thinking shines when they incorporate unique materials or shapes, while critical thinking helps them evaluate performance and predicting outcomes. For example, changing the shape of the wings will have a massive impact on how it flies. Adding weight at the bottom will also have a massive impact, lengthening the blades while also changing their shapes. There's so many things you can do with this particular project. For those students that do require some extension, you can measure and graph descent times, compare aerodynamic properties of various materials, or even design whirlybirds for specific tasks such as carrying lightweight payloads. So the biomechanical hand is a very interesting little project to do. It's a little more involved than doing, for example, a whirlybird or the little catapult. You have to have a few more materials on hand, and you need more time to actually do it and work with those students that need a little bit of extra help in the classroom. Again, we are focusing on year 8s and 9s. Probably not something I would necessarily do with kiddie kids, although primary school kids will absolutely enjoy doing this. Maybe potentially having all the materials pre-cut for them, so they just have to assemble it and then work with it. We're getting into the STEM and curriculum links. So the biomechanical hand aligns with science by exploring body systems like muscles and tendons, obviously by showing how those tendons work to grab and close the hand. Mathematics by proportionally scaling models and analyzing movements. So adult hands are going to be a lot larger than child's hands. So showing them your model and then showing them how the difference in size makes a difference in how strong the model can actually be. For technology and engineering, they apply mechanical principles to simulate human anatomy. Getting into the more interesting things, so intrapersonals, assembling the biomechanical hand requiring patience and resilience, especially for some of the younger students that can get frustrated very easily, as there are some very small components. Another reason I would probably wouldn't do it with students under 6, really, honestly. Students learn self-regulation techniques and reflect on their persistence as a key to success, again, because it can be quite frustrating when it just doesn't want to work the way the student wants it to work. For Global Collaborator, this project introduces ethical discussions on assistive technologies, such as prosthetics, and their impact on global communities. Students can collaborate to design improvements, considering accessibility and sustainability. So there are some really, really amazing things being done by small creators, by 3D printing, biomechanics, and prosthetics. That is a massive thing that we can show the students as kind of an introductory to this biomechanical hand model that they can then build, which can be extended into them building a more sophisticated model if there's 3D printers available at a school, for example, and then showcasing that to their parents and the wider school community. For interpersonal, students work together to troubleshoot mechanical issues, learning to value diverse perspectives and problem solving. The teamwork fosters respect and shared ownership of the final design. A biomechanical model isn't just going to come up from one person. Yes, one person can absolutely do it. It will be a lot easier if the group works together, if you've got more than one head working on something. And teamwork is incredibly important for making things like this work. For critical and creative thinking, students critically analyze how tension and joint placement affects the movement and creatively design solutions for smoother or stronger grips. They might propose innovative features like interchangeable parts or enhanced grip strength. For example, putting something rubber at the tip of the cardboard so that it can actually grip something, or putting a cuff so that you can actually use the thumb properly as well, so that it goes across rather than just sort of down, which is not very anatomically correct. So again, for those students that might need an extension, this project could evolve into exploring robotic hands, analyzing force distribution, or even connecting the model to microcontrollers for automated movement. So really digging into those robotics and ICT skills there, and getting really into the biomechanicals and how a student can make a prosthetic. I know there's some that were made out of Lego, and it would be really awesome to see some of our students do that.